geometry, we are covering PO62, which has to do with inscribed angles. Does anyone know what the word inscribed means? Inscribed. Okay. It essentially means like inside. Okay. And so we're talking about angles that are inside of a circle, but a little more than that. Instead of central angles, where the vertex is at the center of the circle, this time the vertex will be on the circle. So it's an angle with its vertex on, how do I want to say this? On the out, how did I write the other day? On the outside of a circle? I'll say on the circle. Okay? An angle with its vertex on the circle. An example would be something like this. Right? The vertex of that angle is on the circle itself. It's not in the center. It's not somewhere inside the circle, just in a random spot. It's on the circle itself. Okay? Did you get the squeaky chair? Oh, I thought you were trying to fix the squeaky chair. I think that's the squeaky chair. It always disappears from over here and ends up somewhere there. And so the theorems that you need to care about, and the first two have to do with measures of inscribed angles and arcs. Okay? If we have an inscribed angle, okay, we'll call this point P. We'll call this A. We'll call this B. Okay? The relationship here is that the measure Good guys?
No.
Good timing, buddy. All right. The measure of angle APB is equal to half the measure of arc AB. Half the measure of arc AB. So whereas central angles were equal to the arc, inscribed angles are half the measure of the arc. So if this angle looks to be about 80 degrees or so, what would the measure of arc AB be? Joy? 160. Okay? Questions so far? Good. All right. Theorem 10.8 has to do with two inscribed angles that share an arc. So if we have one inscribed angle there, a second inscribed angle here, okay? So we'll call this AB over here again. We'll call this point C and point D, right? So we have angle, I'll let you catch up first. Maybe I'll draw them in different colors here. So we have, right? We have angle ACB, which comes across and goes down diagonally to point B. Then we have angle ADB, right? And notice that both of these inscribed angles, they create arc AB, right? Both those inscribed angles create arc AB. So what do you think is the relationship, or what can we conclude about angles ACB and ADB? Like? They are congruent. Two inscribed angles that create the same arc are congruent angles. Right? Which makes sense, because if I told you that the measure of arc AB was 80 degrees, then asked you for the measure of each of those individual angles, what would they both be? 40, right? ACB is half of 80, that would make this 40. ADB is also half of 80, which would make that 40. Okay? So Theorem 10.8 talks about how to tell if you have congruent inscribed angles. If they create the same arc, then they are going to be congruent. Questions so far? Yes? The triangles themselves, like these here.
Yeah, the triangles that it creates.
Interesting. would those triangles be congruent or not? How could we prove it? What would we need? We would need either side, 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 angle, angle, or angle, angle, side. What do we automatically have here? We have congruent angles here and here because of vertical angles, right? We have congruent angles here and here because of this theorem. Would there be any way to get a side? Because there is no angle, angle, angle for triangle congruency. We do have to have a side. Right? I mean, regardless of which theorem that we use to prove triangles are congruent, we have to have a side length. Is there any way here to say, other than it looks like it, thank you for just getting that out of the way, that we have congruent sides here? Yes. We could use sine, cosine, tangent if we knew that this was a right triangle here. So we'd have to have some way to say that it would be a right triangle, because right triangles are the only ones that we can use sine, cosine, tangent with. Blake? I mean, we have theorems for congruent chords, right? AC and DB are both chords. One of the ways we talked about to prove chords congruent would be if we can somehow say that CA is congruent to DB, then the chords would be congruent as well. But I don't know if we have enough information to say that. Enough information to show that these triangles are right triangles, so using something like sine, cosine, tangent wouldn't be an option. I don't think we have enough information here, you know? And sometimes that's what geometry is about. It's looking at what we know, and is there enough here for us to do something with it? And I just don't think there is enough here. Are the triangles similar? Because of angle, angle, yes, they are similar, but that doesn't necessarily mean we have congruent triangles. Yeah, like.
If there was like a center point out here, could we tell if it was
Like if if CB and DA were diameters. We're talking about, because with diameters of a circle, that's where you get that right angle relationship, potentially. But the center of the circle would probably be right about here-ish. I don't know if that helps us any there. Okay. Great question. Okay. Yeah. Michael.
How do you know the center is there?
I just guesstimated. It looks like that's where the center is. Happy? Has that fulfilled your math experience?
Not the thing about yesterday.
Okay. Moving on. Oh, I forgot we were on the math. I gotta hurry up. Moving on to inscribed polygons. An inscribed polygon is a polygon with its vertices on the circle. That doesn't look like the word vertices. There it is. A polygon with its vertices on the circle. So an example, here's a circle, here's a point, here's a point, here's a point, here's a point. All right, that would be an inscribed polygon. All right. Another example with an ovalish circle, we'll make it a pentagon in there. Right? There would be an inscribed pentagon. So it's a polygon with its vertices on the circle, which, every vertice with those sides coming out, we've got a whole bunch of inscribed angles here, right? So inscribed polygons can help us look. We can know what their measures are based on the inscribed angles. Theorem 10.9 has to do with right triangles inscribed in a circle. if you have a right triangle inscribed in a circle, let's try and do my best to make a right angle here. We'll go like this, across like that, right? How do you know it's a right angle? That's a good question, okay? What do you suppose the relationship is between the hypotenuse of a right triangle and a circle? Peter?
The hypotenuse is the diameter?
Yes. If you have a right triangle inscribed within a circle, the hypotenuse of that triangle is the diameter of the circle. Okay? So in words, the hypotenuse of an inscribed right triangle will be the diameter of the circle. The hypotenuse of an inscribed right triangle will be the diameter of the circle. So, if you know that the triangle is a right triangle, if you're given the right angle, you then know the hypotenuse is the diameter. If you're given the diameter, if you're told this is the diameter, and it's a triangle, you can then conclude that it's a right triangle. So it goes both ways. If you're given one piece of information, you can conclude the other. If you're given the right angle, conclude the hypotenuse is the diameter. If you're given the diameter, you conclude the angle is a right angle. Okay? Which, of course, brings back all the Pythagorean theorem, sine, cosine, tangent, things like that we learned previously. They could pop up again here. Okay? Theorem 1010 has to do with, who's snorting? Oh, Gino. Do you agree to the terms and conditions of staying in the classroom today?
Yes.
Do you think that snorting is a term and condition for being in the classroom?
Do I get a warning? Is this my warning?
Yeah,
Okay.
Yeah.
I'm done.
you're done snorting.
Done.
Okay.
Done.
Whenever you feel like doing something, just ask yourself, do I think this is in the terms and conditions of staying in the classroom?
Okay, you should
And
know.
the answer is no.
I'll ask myself the condition.
You're in eighth grade. You should know the terms and conditions.
You print it out.
You know what to expect.
Yeah,
but you don't know.
Yeah, print it out. and take-
Like, if I did print them out, like you read them anyway. No one reads the terms and conditions. Well, you read all.
Make everybody spin it.
Okay. Theorem 1010 has to do with an inscribed quadrilateral. Okay, so we're going to put 4 points here. That looks like a good quadrilateral. Like this, like that. Not quite a square, no. If that was a square, it'd be the worst square I've ever drawn in my life.
That's the best square.
Okay. And Theorem 1010 says that an inscribed quadrilateral, I missed a couple letters. Will have opposite angles that are supplementary. Okay? An inscribed quadrilateral will have opposite angles that are supplementary. An inscribed quadrilateral will have opposite angles that are supplementary. So, how is this helpful? Well, if you're told that this angle here is 80 degrees, and what would the opposite angle be? 100, right? Because they have to add to be 180. Furthermore, if I labeled this point A and this point B, and I will need to label this point C as well there, what would the measure of arc ACB measure? Remember we talked about with inscribed polygons, those vertices on the circle do create inscribed angles, right? If we know that this bottom angle, we'll call it point D here. If we know that angle D is 100 degrees, what would the measure of arc ACB be? Drake. 200, right? Because this angle creates arc ACB, right? And the angle is 100, which is half of the arc measure. Therefore, the arc measure will be 200. So there's relationships all over the place with central angles, inscribed angles, things such as that. All right. Questions, comments, concerns, complaints, comments, congratulations, criticisms on theorems 10.7 through 10.10. Yes, sir.
Congratulations. Those are some good circles.
Thank you. Thank you.
Because it
My
looks
circle
like-
game is
it looks
reaching
like it.
its pinnacle. Yeah.
Yeah, yeah, bro.
I have Excedrin, but I couldn't give it to you anyway. So
Can I have
no.
some of your drugs?
You may not.
Do you have penicillin?
Let's finish our drug conversation. Might throw it off. Do you need to go down to the nurse, Joe?
My head hurts.
Is it I'm talking too loud? I'm sorry. I get really excited about circles. Sometimes I talk in circles just because I'm so excited about it.
I'm seeing,
Oh,
I'm
I
seeing
agree.
shapes.
Your eyes are what?
My eyes.
Huh? No, just my head hurts.
Do you want to go down and get some?
I'll go get a drink.
I can walk
Okay.
down.
No, it's fine. I'm sure he'll manage.
Why'd you wink?
I'm hallucinating.
I didn't wink.
He's gonna go get some lemonade.
I think I'm
All right, 3, 2, 1. You are quiet. To minimize your homework tonight, let's get through some of this today during class. Find the measure of the arc or angle. Raise your hand if you can tell me with confidence the measure of arc QT. Okay, first of all, identify what is arc QT. Arc QT is there. And then take a look at what I know. Right? What do you know about arc QT? Look at the angle that makes arc QT. Thomas, what do you think? Too busy talking. At least you're honest. I appreciate that. Do you think that talking to Joey and drawing on his page is part of the terms and conditions?
Yeah.
No, it's not part of the terms and conditions. So stop. What's the measure of arc QT, Joey? 100. The inscribed angle that creates it is 50, and so arc QT would be double that, making it 100. Okay. Arc RTS. So let's look at arc RTS since it's angle RTS. Angle RTS goes from point R to point T and over to S. We're looking for that angle measure right there. Take a look at the other information in the diagram. What do we know? What's the relationship? Peter? Not 50.
Well, it looks like it.
It does not look like 50 to me.
Tiny.
I'm just saying. Step up. 24. Okay? It is 24 degrees, and we know that because the angle is half of the arc that it creates. Because arc RS is 48, that angle RTS is going to be half of that, 24. Okay? Angle RTS. We're now on the second figure here. Angle RTS. RTS goes from point R up to point T, over to point S. Look at what we know. Look at what we know. Mackie,
It's 31
how do you get that?
because 31 makes RS 62, and it also lines up with the other one.
Good. So that angle 31 there, angle RUS, creates the arc SR, which we know is 62 because it's double the inscribed angle. Well, it turns out that arc SR is also the arc created by the angle that we want, RTS, which according to theorem 10.8 means that those angles are congruent. So RTS will be 31 degrees as well because they create that same arc on the outside of the circle. Arc RUS, because this is a three-lettered arc, we know it's a long way around. Major arc RUS. That's some good tracing right there. And what's the measure of arc RUS, Seppa?
298.
And how do you get that?
Subtract 62 from 360.
If the whole circle is 360, which is given, and we know that part of it is 62, 360 minus 62 gives us 298, right? Because if we know part of it and we want to know the rest of it, that means that the part that we know plus the part that we want has to equal the whole thing. And so it is solving for the variable to get to that 360 degree. So 360 minus 62. Lastly, looking at an inscribed polygon. Arc KJM. Arc JL. Arc LMJ. Take a minute and work with the people around you, and we'll come back to it shortly.
Not yet.
What do you know about it?
I got
So inscribed polygons, inscribed quadrilateral. Maybe check out Theorem 1010. Maybe check out Theorem 1010. If you're stuck, look at Theorem 1010. Because we have an inscribed quadrilateral here.
This KJ, I'm wondering, so would it be 2A
If you're stuck, look at Theorem 1010, where we talk about inscribed quadrilaterals.
Oh.
Theorem 1010, inscribed quadrilaterals.
But it being a
That's why I wanted to answer.
alright.
It's gonna be 160.
Trust me.
Right? That's all I put 45 over 80. That'd be right.
Got it.
What?
Thank you, Joe.
Oh, then it'd be 120.
I miss you.
So your hint here was to look at Theorem 1010, which is where we talked about an inscribed quadrilateral, and the relationship was opposite angles are supplementary. So the challenge here was, how do I solve for A, how do I solve for B? Well, knowing that opposite angles are supplementary, one equation you would set up is 2A plus 2A equals 180. Oops. And then your other equation is 4B plus 2B, or not 2B, yes, equals 180. Did you get it? Oh, the Shakespeare joke. So A is equal to 45 after solving that, and B is equal to 30. So then you can put those values in there, and if A is 45, then this is 90, this is 90 there, this would be 120, and this would be 60. You add all those up, you get 360, which you should because it's quadrilateral. Quadrilaterals all have 360 degrees. And then you look for arc KJM, knowing it's a major arc from K through J to M. And then noticing that it's this 90-degree angle that creates that arc. Therefore, KJM would be 180. Double that. Okay. Arc JL, which goes from here to here, is the arc created by the 60-degree angle, angle M. It'll be double that 60, which makes it 120. And then finally, arc LMJ, which being a three-lettered arc is the major arc, LMJ around there. Okay. Two ways to look at it. Knowing that JL is 120, we can subtract 120 from 360 because we want the rest of the circle, right? Or, since this 120 creates arc LMJ right here, we can double that, and either way, we get 240. Look how colorful this objective is. I love it. Good stuff. Okay. Your assignment.
No.
Wait.
On page
I have a great Francis Bacon book for you. Please, can we not?
676, I would like you to do 3 through 8. Page 676. 3 through 8 and 13
You a test
through 15. 3 through 8, 13 through 15. 9 questions. You can do this. That's how I math, folks. Thanks, everybody.
You always pick your